Welcome to video number 14 for Physics 102. This video contains more information about elastic collisions. By the end of this video, I hope that you understand that by using variables, it's possible to determine what happens during any general elastic collision in one dimension. Let's begin by reviewing what is an elastic collision. As discussed in class, an elastic collision is one where, in addition to the momentum being conserved, the total kinetic energy is also conserved. So we always have that momentum is conserved vectorially in any collision. So we have the sum of the vectors pi must be equal to the sum of the final momenta pf. In an elastic collision, we also have that the sum of the kinetic energies ki before the collision must be equal to the sum of the kinetic energies after the collision, sum kf. This is only going to be true for elastic collisions. Here's an example of some elastic collisions, in that you can see that the balls basically return to the same height after every collision. This tells us that after each collision, the kinetic energy is conserved, because all of that kinetic energy is transferred into potential energy. So this is a good example of some elastic collisions. Let's think about two objects colliding elastically in one dimension. We're going to tackle this problem in a slightly different way. We're going to try and solve the most general case of an elastic collision between two objects in one dimension, and then interpret and apply those results. Here we have two masses, m1 and m2, that are going to collide elastically. What you're looking at is a snapshot before the collision. The mass and the velocity of each ball before the collision are given. The question is, what is the velocity of each ball after the collision? We are going to assume that the balls stay in one dimension. We know that momentum must be conserved, as in all collisions. So the sum of the momenta before must be equal to the sum of momenta after. Since we're only working in one dimension, and I will call that direction x, we can replace the vector sums with sums of just the x components. Initially, we have the mass of the first ball times its initial velocity, plus the mass of the second ball times its initial velocity. Similarly for after the collision. Conservation of momentum says that these two quantities must be equal to each other. Since this is all happening in one dimension, and we already have a lot of subscripts, I'm going to get rid of the little subscript x. We know that everything is happening in the x direction here, and this just makes it cleaner to look at. Since this is an elastic collision, we know that the kinetic energy is also conserved. Written mathematically as the sum of ki must be equal to the sum of kf. Initially, we have 1/2 m1 v1 squared initial plus 1/2 m2 v2 initial squared. That's our initial kinetic energy in the system, the sum of the kinetic energies of the two objects. Similarly, we have the kinetic energy after the collision. We don't know what v1f and v2f are yet, but whatever they are, they will just go into our expression for kinetic energy, and we will add these two kinetic energies to get the total. For an elastic collision, the kinetic energy is conserved, so we can place the initial kinetic energy on the left equal to the final kinetic energy on the right. So now we've got these two equations for this collision. The top one based upon conservation of momentum, and the bottom one based upon conservation of kinetic energy. We also have two unknowns. We have the final velocity of the m1, v1f, and the final velocity of m2, v2f. Now you can see that we have two equations and two unknowns, and that we can solve this as a system of equations for v1f and v2f. While the algebra gets somewhat tedious, the results are here, and will be provided on your equation sheet. Note that you can only use these equations if the collision is in one dimension and the collision is elastic. If the collision does not meet these requirements, then you cannot use these equations. Let's think about understanding and interpreting these results. In the picture, we have V1 going to the right and V2 going to the left. However, none of the math that we have done up to this point makes any assumptions about the directions of V1 and V2. This means that all the directions should be taken care of as long as we're careful to input everything correctly. For that, we need a coordinate system. I'm going to choose a coordinate system that has x going to the right, like this. In this particular system, V1i is defined to be positive, and V2i is going to be negative. If I use these positive and negative signs in these solutions, everything will take care of itself. What do I mean? I mean that if you solve this for V2f, and you happen to get that V2f is greater than 0, it means that after the collision, M2 is moving in the positive direction, which we have defined to be to the right. In your quiz, you will involve solving for V2f and V1f, given some initial conditions, and interpret those results. This concludes this video.